So, is that all we need? Suppose you have the mechanism to carry out the invalidations. Will that work? Let me give you another hint. Think about if you have several stations, A, B, C, and you have a train from A to B that's going to take 2 hours, train from B to C, 2 hours. How long does it take to get from A to C? Put this way, it shouldn't be a surprise that it depends. It could be faster than 2 hours plus 2 hours. It could be slower than that because of congestion. It really depends. Now, can you think of a scenario in terms of sending messages? It's really, train is a good analogy for these packets. They go from one place to another. There are congestions in the network. Can you think of something that can break our intuition? So this problem is called the memory consistency problem. And it has to do with the intuition, the mismatch between the intuition and the underlying reality. The intuition is pretty, but the underlying reality is ugly. It has all these implementation tricks that which we use to make system run faster, and as a result, system is not as simple as we'd like to believe. So what's the intuition? Execution follows sequential order in a single program, and this ordering is transitive. So if one action A happens before B and B happens before C, we think it's obvious A happens before C. So let's look at this particular code. I have 3 threads running on processor 1 to 3. Processor 1 is simply triggering the loop to processor 1 simply updates variable A to 1. And in many of these kind of examples that we will show subsequently, we'll always assume variables are initially all 0. If we look at code on P2, it's simple spinning loop, waiting for A to become 1. And when that happens, we break out of the loop and set B to 1, which in turn releases P3 from its spinning loop and execute the statement print A. So because of the program order, we would think A1 is happening before the loop happens before B is what make the loop finish, and the loop precedes A. So by the time we print A, we obviously expect it to not be 0 anymore. It would be 1, or it could be something else if there's another thread that updated A. And the reality is there are lots of overlapping and even out of order events on the system level to make things go faster. So different processors can see things in different order. And we may have a system where A is not 1. And for very simple reasons. Pause a minute, pause the video, and think about it and see if you can construct a scenario. And I'll do that in the next slide. Here is the case where suppose we execute the 3 threads that we saw on the previous slide. Here in this system, it doesn't really matter where P1 execute, but P2 and P3 executes on these 2 nodes. And the invalidation that we've been talking about is usually handled by what we call the home node of a particular line. The exact detail doesn't matter. We will get to that later when we look at directory-based protocol. But for now, just assume this node over here is where the invalidation messages are all issued from. Okay, so you can see the invalidation would go to P2 and P3, assuming they each have a copy in their cache. And this invalidation, in this particular example, can go through different routes. The counterclockwise route in black, and the clockwise route that's a little bit more congested, shown here in dashed line. And because of that, they can arrive at different timing. Now I'm going to show a little bit of an exaggerated cartoon, Disney quality cartoon, and you see how this goes. So if A equal to 1 is issued by P1, remember what we said. If we run an invalidation-based protocol, we need to invalidate anybody that has a cache line in their cache, has a copy of cache line that contains A. And let's suppose home node knows that. It knows one of them is P2, the other is P3, and we'll send 2 invalidation messages to say, please shoot down your node, your cache line, and it will happen like that. Okay, you see, on the not so busy route, everything happens fast. We invalidated the node, and then P2, because it's running a spin loop, will therefore issue another request. It will read and incur a cache miss, goes back to home A, try to get the value, got the value, finishes, writes B equal to 1. I mean, all of this, all the black arrows are done before the invalidation finally reaches P3. So if this is really happening, then by the time we finish even the loop over here, we haven't invalidated our cache line of A in P3. And so if we finish that and come out, what do we expect? We expect A to be the previous value, which is assumed to be 0. So it's perfectly logical to expect this system, with the support that we described, that invalidate the cache coherence support, the mechanism to shoot down cache line. We have that mechanism to shoot down cache line. It's implemented correctly. Still, at the end of this execution, in this exaggerated case, we could print out 0. And the programmer would be looking at this and say, doesn't make any sense. My code is right, doesn't have any error. The hardware must be wrong. So that is the problem of memory consistency. So why do we call that memory consistency problem? Because, okay, let's say this particular example, how do we fix it? Is there a way to fix it? If we look at the source of the problem, why is it that we have this problem? It's really an issue of what we would call the atomicity, and in particular write atomicity illusion, that we think we have this statement over here. If we executed A equals 1, it's 1. Everybody should know that it's 1 now, that it happened in a point in the time axis. But that's actually not true, as we can see that the accomplishing this writing A equal to 1 really involves sending invalidation messages. And it's therefore relative, depending on how far you are, how congested the network is, between the node issuing the invalidation and the node receiving it. So it may happen at 2 different time points. Okay? But our intuition is assuming that this is a statement. It executes, it executes. Okay? So how do we solve that problem? Well, one solution is this, and later on we will explain that this is actually called the sequential consistency. It says, well, hold on, this is what's really happening. There are too many things that happen simultaneously. So let's make sure that they cannot do that, that one event happens before the next event can start. Okay? Typically we represent that as the sequential consistency as a box like this, where you have processors and there's a memory, but the memory is really time multiplex among the processors. At any time there's only one node that can do something to the memory system. So for instance, when A is 1, this memory transaction is happening, we will not allow another transaction to happen, which is B equal to 1, until we make sure the previous transaction is done. What does that mean? What does done mean? And you will see in textbook and technical writing that sometimes it's referred to as accomplished with respect to a node. So A writing to 1 is really done with respect to a node when you invalidate the older version of the cache line. If you invalidate it, that write is done as far as you're concerned, okay? Because you wouldn't be able to see the older value. If you read from your cache, you have to suffer a cache miss and therefore go get the most recent value, and you will get the newer value, not the old value. So that's done. So how do we solve this particular problem? B equal to 1 cannot be allowed to happen until both P2 and P3 have finished their invalidation. So how do we know that they finish invalidation? If they send out acknowledgement receipt and we collect enough, we sent out 3 invalidation requests, we got 3 receipts back, okay? All 3 have finished invalidating their version. No old version still exists in the system. We can say at that point we know it's done globally with respect to the entire system. So that's one way to solve the problem. When you do that, the particular example that we just showed, this particular code, it will not print out 1. It will not print out 0 here in this statement. So you won't see that effect. Okay. Easy. We solved the problem. Yes? Well, actually, no. It's not necessarily a problem that needs to be solved. It's more of a trade-off. The reason we allow things to happen simultaneously, again, is to make things go faster. And if we have such a restrictive model, at the beginning at least, people thought then it really kind of slows the system down, and perhaps to the point of defeating the purpose of making parallel processor. After all, we want maximum concurrency. We want lots of things happen at the same time so that execution is faster. And if we're being so restricted as to what we can do, the system wouldn't be as fast as we would like. So that led to some models being proposed that are weaker. The idea of weaker consistency model is to allow the system designer, the hardware designer, to use more tricks to improve concurrency, parallelism, and therefore performance, without messing the illusion too much. So it's usually exploiting certain things to say, well, if you can only do this, then I can do this, and the system would run faster. Here's a motivating example. Let's say we have sequential consistency. What does that mean? When we're executing a memory transaction, we have to wait until it's completely done before we allow the next one to continue. So let's say this is a very common producer-consumer type of code pattern. P1 over here is producing a whole bunch of data 1, and when we're all done, we say, now you have the entire record ready, you can read it, it makes sense now. And P2, on the other hand, would wait for the flag to be ready before it starts to read from the data that it was supposed to receive. Okay, so this happens. Now, if you have sequential consistency, this would be your timing. Well, update to data 1 would take some time. This may be a long time. Too bad. You have to wait. You wait for the entire latency before you can start writing to data 2 and so on. So this will be completely non-overlap, and it's very slow. What's the alternative? The alternative is to recognize, okay, as far as these two threads are concerned, we really don't care about the consistency before the flag is exchanged. Okay? Before P1 flags down P2, now you can continue. So why not allow, let's say, the data to access in some concurrent fashion? Okay? Knowing that we're not going to read them anyways until we read flag. So this timing on the right hand side would be a lot faster. Okay? So if we can do this, then the system would run faster. But this depends on you, the programmer, give us some mark in the program code to say, well, this is special, you can do it. That's special, you can do it. At certain place, you can relax these consistency considerations as long as you do things right at these points. They're sometimes referred to as synchronization points, but that's the idea. That's the general idea of a weaker consistency model. In a sense, we're no longer guaranteeing the system is consistent at every time point. We're guaranteeing that at certain time point of interest, they're going to be consistent, meaning everybody agrees what the value of a certain location was. Unlike in the previous example that we showed just a few slides ago, you can say that the view is inconsistent because, for instance, in the example that we show here, right? Really, at the time of printing A, P3 had a different opinion of its value from everybody else, from P1 and P2. So that was the idea. Oops. Now, if you program this system correctly, meaning you correctly identified what are synchronization points, then your program is going to still behave according to the shared memory illusion. It would work fine. It would produce the intuitive result. But if you make a mistake, so in the case that we're showing here, for instance, this would require you to somehow, for instance, label that flag this is special. At that point, you need to make sure the system is consistent. If you fail to do these things and your program execution leads to counterintuitive result, that's your problem, the programmer's problem, not my problem, the hardware designer's problem. That's actually the problem for weaker consistency models, that the contract is not necessarily clear and we would have some form of bug